Hello, this is Dr. Johnson. I'm one of the AP Stats teachers at Capel High School, and I want to welcome you to this lesson on significance tests for a population mean. You will need your calculator later on in these slides, so get that handy. First thing I want to do is I want to review with you the type 1 error and the type 2 error, and in the context of the boy who cried wolf. You might remember this as one of Aesop's fables. Let's say that the null hypothesis is that there is no wolf. The alternative is that there is a wolf. So what is a type 1 error? In a type 1 error, the null is true, but we believe otherwise. So here's the type 1 error. There is no wolf, but we mistakenly believe there is one. And what are the consequences of that? Well, the townspeople run and check it out, but find that the boy is laughing at them. What is a type 2 error? In a type 2 error, the alternative is true, but we believe otherwise. So in this case, there is a wolf, but the townspeople don't believe the boy when he cries wolf. So the townspeople don't run out and check it out, and the boy eats some sheep. This brings us to the topic of this slide presentation, and it is power. Power occurs when there is a wolf, and we correctly believe that there is one. In statistical terms, power is the ability to correctly determine that there is a wolf when there is one, or to correctly determine that the alternative is true. The power of a test is the probability the test will correctly reject a null hypothesis when a specific alternative is true. The power of a test is inversely related to beta, the probability of making a type 2 error for that alternative. So the relationship between power and beta is this: power is equal to 1 minus beta. So on an exam, we can tell you beta and ask you to calculate power, or we can tell you power and ask you to calculate beta, and then we'll ask you to interpret both power and beta. Another way of saying this is power is the probability of correctly rejecting the null hypothesis. And there are many ways of expressing power in symbols. So one way of saying it is that power is the probability of avoiding a type 2 error. Power is equal to 1 minus the probability of a type 2 error. Power is equal to 1 minus beta. And I've summarized it here, all of the relationships in this equation in red at the very bottom. And now I want to show you what power looks like in a graph. So suppose that the blue distribution is the distribution associated with the null hypothesis being true, and the red distribution is associated with the alternative hypothesis for some value being true. If you set your cutoff, if you set your critical value at alpha divided by 2, say you're doing a two-tailed test, and you set your cutoff at alpha divided by 2, then I draw a line at that cutoff, and the power is the area under the orange curve that is to the right of the dotted line. And that's representing the power of that test. It is the probability of correctly rejecting the null hypothesis, or correctly determining that the alternative is true when in fact it is true. Now you remember this table here, I've just added a little bit to it. As before, columns are the states of nature, so we have either the null being true or the null hypothesis being false, and the rows are the decisions. We either reject the null or we fail to reject the null. In the center there we have type 1 error. Type 1 error, probability of a type 1 error is alpha, so I've put that in. In the bottom right we have the type 2 error, that is the probability of a type 2 error is beta. And now in the upper left I've put power there. So power occurs when you reject the null hypothesis and the null hypothesis is false. Okay. This tree diagram right here tells us the same thing as the table on my previous slide. If this tree diagram makes more sense to you, then this is what you should use for review. Now I want to show you power using these two different graphs right here. Power is a conditional probability. The power of a test is conditional upon what the alternative value of the parameter actually is. So on the right-hand side, I have lots of overlap and much less power. So in essence, the more overlap we have between the two distributions, the less is the power value. Okay, the graph on the right would be considered noisy data because it is harder to detect the difference between the two distributions. So the distributions are, the data is considered noisy. Our test is not always good at determining when the null alternative hypothesis is true. Now let's look at the graph on the left. Here we have less overlap and greater power. If there is no overlap, the power would be 1 and the beta would be 0. Power is a probability that depends on what alternative value the parameter mu has that we are interested in. Unfortunately, we do not often know the distribution associated with the alternative hypothesis. So oftentimes, we don't know much about where that orange graph is. Now let's interpret power. Suppose you want to test the average height of students at Capella High School using the null hypothesis that the average is 65 versus the alternative that it is greater than 65. So we have a one-tailed test. Suppose also that the true mean is 67. So that we should reject the null because the true mean is greater than 65. And we say that the power of the test is 0.8. So now let's interpret the power value, 0.8. Given that the true mean height of students is 67, there is a 0.8 probability of finding convincing evidence that the average height is greater than 65 inches. So power is conditional, so we have to begin with this given. So if the true mean height is 67, there's a probability of 0.8 of correctly rejecting the null hypothesis. Okay, that's the interpretation of power. You are expected to know that. Beta interpretation. So we're going to do the same thing, but this time I'm going to interpret beta. Same null hypothesis and alternative. Suppose also that the mean is 67 and the power is test is 6.8. First thing I do, what is beta? Well, if you know the power of the test is 0.8, then beta is 1 minus power, or 0.2. Now interpret beta. What is beta? Here it is. Here's my interpretation of beta. There's a probability of 0.2 of not finding convincing evidence to believe that the average height is greater than 65 when in reality the average height is greater than 65. Okay, so 0.2 probability of failing to reject the null when we actually should have rejected the null. Few points about power. Power of a test against a specific alternative value of the parameter is always a number between 0 and 1. A power close to 0 means the test has almost no chance of correctly detecting that the null is false, so there's a lot of noise in the data. A power close to 1 means the test is very likely to reject the null in favor of the alternative when the null is false. Now I want to talk about what are the things that you can do to increase the power of a significance test to detect when the null is false and the alternative is true. I have listed 4 things, and I think this is pretty much the best 4 things you can do. Increase the sample size n, and really increase sample size as much as you can afford. Increasing the sample size decreases the spread of both the null and alternative distributions. So on my previous slide, that the orange distribution gets skinny and the blue distribution gets skinny as well. So increasing the sample size decreases the spread of both the null and the alternative distribution, which decreases the overlap between these distributions. So just a little bit more, If one wants to both decrease alpha and beta at the same time, then one has to increase the sample size. But gathering more data might be more expensive in terms of time, money, and resources. So what's the second thing we can do to increase the power of a test? Increase the significance level alpha, that is, increase the cutoff. But this has a downside. It increases the probability of a type 1 error. So it's not a perfect solution right here. The higher the significance level, the greater the power, but that's only because the test becomes more lenient, that it becomes more favorable to getting an alternative hypothesis. The third point, increasing the difference or the effect size between the parameter value under the null and the alternative hypothesis. Now, what am I talking about here? I'm saying that big effects are easier to detect than small ones. If the two distributions are far apart, it makes it easier for me to detect a difference. That should come as no surprise here. However, it is not always possible to manipulate the difference between the mean values under the null and the alternative hypothesis. Sometimes we just can't control Mother Nature. And the last one is we can decrease the standard error, but this requires typically a different way of gathering data. So we can reduce the variability, noise in the data by using paired data, a block design, or a stratified random sampling, or other design improvements. So that would be ways to decrease standard error. And here I have a meme for you. I heard you up your sample size, more power to you. That's one certain way of increasing power. So I want to talk about the difference between practical versus statistical significance. I think I talked about this in an earlier presentation. Statistical significance and practical significance are not the same thing. A small but important real-world difference may fail to reach significance in a statistical test, and this has potential downside. A lot of good studies go unpublished because they fail to reach an alpha level of 0.05. On the other side of the coin, a finding can be statistically significant without being practically important. So, based on a large survey of households in the US, they found that the proportion of households with a pet cat differs significantly from 1/3, but is actually quite close to 1/3. So there's a statistically significant difference, but in the final analysis, who really cares? So the practical significance is a question of, do you really care about the difference? So let's talk about doing an FRQ test involving a test statistic and testing a population mean. First thing we have to do is we have to write out our null and alternative hypothesis. The null hypothesis will be that first thing you have to do is define mu. And then your null hypothesis is that mu is going to be equal to some hypothesized value. Then you have to determine what is your alternative hypothesis. If you're doing a two-tailed test, you're going to use the not equal sign. If you're doing a one-tailed test, you're going to do the strictly less than or strictly greater than sign. I should caution you that you need to make sure that you do not switch up the null and the alternative hypothesis. If you switch these up, you're not going to get credit. So those are the null and alternative hypothesis for a test of difference in mean of means. Then we have to check our conditions. As usual, we check the random condition. If the data is not random, we have to toss it out because we have a potential for bias, and we cannot fix bias with good mathematics. We have to start over with our data gathering. Second thing we do is we have to check for whether the data was independent, our observations are independent, or whether the 10% condition is satisfied. When sampling without replacement, we need to check that the sample size n, lowercase n, is less than or equal to the population size divided by 10. And again, you actually have to do this. You have to use information from the problem to test these conditions. It's not enough to just say that the conditions are met or put a check mark next to them or name the conditions. You actually have to test the conditions. The last condition is that the population is normal or your sample size is large. So the population has a normal distribution, or the sample size is greater than or equal to 30. That will satisfy this condition. If the population distribution is unknown and the sample size is less than 30, then you can use a graph of the sample data to assess the normality of the population distribution. So what types of graphs am I talking about? Box plot, dot plot, stem and leaf plot, histogram, they all work. A normal probability plot might work as well. But if you so once you graph it, you're going to look to see whether the graph shows strong skewness or outliers. If the sample size is less than 30, do not use a Z or a T procedure if the graph shows strong skewness or outliers. If the graph does not show strong skewness or outliers, then you can say a couple things. One, you can say it's okay to proceed. That's fine. Or you could say it is reasonable to believe that the sample is drawn from a parent population that is approximately normal. The key here is that you need to get back to the idea that the parent population is normal or approximately normal. So let's talk about a Z-test for mean. This is rarely used. When the population standard deviation is known and the conditions are met, the standard Z-test statistic is this right here. And the Z, of course, the Z statistic will follow a standard normal distribution, and you use your calculator to figure out the probability. But we rarely know the population standard deviation, so this formula is seldom used. Instead, we're going to use this type of sampling distribution. When certain conditions are met and the population standard deviation sigma is not known, the sampling distribution of the statistic x bar has a mean of mu and a standard error equal to the sample standard deviation divided by the square root of the sample size. And again, the standard error is interpreted as the typical distance between the mean of the data and the true population parameter mu. And now we get to our t-statistic. The t-statistic, rather than a z-statistic, is used when making inference about the population means when the standard deviation of the population sigma is unknown. And this is the more likely case. And here is our t-statistic right there. And same thing here. For one quantitative variable x that is normally distributed, the standardized test statistic is equal to the sample mean divided by the population mean, sample mean minus the hypothesized value divided by the sample standard deviation over the square root of n. That on a numerator there is the hypothesized value. And whenever you're working with the t-distribution, you have to report the number of degrees of freedom. And in this test, the degrees of freedom will be n-1. So when do we use the z-score and when do we use the t-score? Let's review. Use the z-score when making an inference about a proportion. Every time you have a proportion, we use the z-score. Also use the z-score when making an inference about the mean when the standard deviation is known, but that occurs rarely. Use the t-score when making an inference about the mean when the standard deviation sigma is unknown. So let's practice with this, and here's where I want you to get out your calculator. 2 students like to eat Subway sandwiches. However, they noted that the length of the 6-inch sub sandwich that they get at their favorite restaurant seems shorter than the advertised length. To investigate, they randomly selected 24 different times during the next month and ordered 6-inch subs. Here is the actual length of each of the 24 sandwiches in inches. So, since we have a sample that has a sample size less than 24, we know we're going to have to graph this data. So what I want you to do right now is pause the video right here and go to your calculator and put these 24 numbers into list 1 on your calculator. So go to module number 2, the statistics module, and then you should see list 1. Put all 24 of these numbers in list 1. You might have to pause the slides right here. I'm going to proceed, so when you're done, just move forward. So the question is this: do the data provide convincing evidence at the significance level alpha equal 0.1 that the sandwiches at this restaurant are shorter than advertised on average? Okay, so it says shorter than average advertised, so I know we're going to do a one-tailed test. So the first thing we do, we write out our identify section. And in the identify section, you're going to define your parameter, tell me the significance level, and write out the null and alternative hypothesis. So let mu be the true mean length of a 6-inch sub from this restaurant. That's how I'm going to define the parameter. We want to test the following hypothesis at alpha equals 0.1. And the null is that they are equal. The alternative is that the true mean is less than 6. So my hypothesized value is 6 in this problem. So next thing we do is we check our conditions. In the first line of that, I want you to name the procedure. The name of this procedure is called a one-sample t-test for mu. If the conditions are met, we will perform a one-sample t-test for mu. We need to check the random condition, and indeed they randomly selected 24 different times during the month. So we're going to say that this was random selection. We need to pass the 10% condition. It is reasonable to assume that this restaurant makes more than 10 times 24 or 240 subs in a month. Now here's where we get tricky. Because the sample size is 24, and that's less than 30, and we do not know the shape of the parent population, we're going to have to graph the sample distribution. Now it says here I drew 2 graphs, but I only drew 1 really. And I look at that graph and I say, no strong skewness and no outliers, so we're going to pass the test. So when you pass the test, there's only a couple things that you can say. One thing is this: it is reasonable to use the T procedure for this data. Or you could say it is reasonable to proceed. Or you could say that it is plausible that this data came from a parent population that was approximately normal. Those 3 statements are correct. And then you can move on. So now we're back to our calculators here. From the main menu, go to the statistics module. That's module number 2. And we're going to enter your data in list number 1. We're going to press test. That's F3. What type of test is it? This is a t-test. So we hit F2. What type of t-test is it? It is a one-sample t-test. So we hit F1. Now, our data is coming in. We're inputting our data through a list. So I put on the top, data says list. It is a one-tailed test, so I have to make sure that I have the strictly less than my hypothesized value there. My hypothesized value is 6 because I wanted to see whether it was less than 6. The data is coming from list 1, not list 2 or list 3, so you have to pick list 1, and the frequency is 1. Now, if I didn't give you the data, I would have to give you a mean, a standard deviation, and a sample size. And if that was the case, then on that first row, you would hit var, and you'd have to add the mean that I give you, the sample standard deviation that I gave you, and the sample size. And you'd still be able to get to the same conclusion. So you hit execute, and it returns the t-statistic, the probability, the sample mean, and the sample standard deviation. Okay, so write those things, all that down. You might get partial credit just for writing the output from your calculator. So we're going to write that down. Now we're going to go to onto the calculate part. So I write again, the sample mean is 5.68 inches. The sample standard deviation is 0.66 inches. And now I want to write my t statistic. So here's the formula, x bar minus my hypothesized value divided by s over the square root of n. Now I don't have to write the formula in symbols, but I do have to write it with the numbers from the problem in it. So there I've written the formula with the numbers from the problem in it, and I take my calculator and I confirm with my calculator that it is equal to 2.41, And that is the exact same number that I got using the procedure that I described earlier. So things are looking good. Now I draw a t distribution, not a z distribution. I'm drawing a t distribution. And I know that my t statistic is minus 2.41 standard deviations below the mean. So I go to that. I draw a borderline at 2.41 standard deviations below the mean. And it's a one-tailed test, so I shade an area less than that border. I labeled it this time with my population values 6 and 5.68, but I could have labeled it with my t distribution values of 0 and minus 2.41. That would have been perfectly acceptable. Now I want to do our calculator work. So we know the p-value, so you could just write from what we know from what we did before. You could just write down that last sentence. The calculator's one sample t-test for the mean with degrees of freedom 23 reveals a p-value of 0.012. That would be fine. Okay, but remember, with the t-statistic, you always have to report the degrees of freedom. Or you could do what I have here with my calculator notation for the TCDF function. So I wanted to find out what is the probability of getting a random t less than minus 2.41. So TCDF, I set my lower value at minus 1,000, my upper value at minus 2.41, and my degrees of freedom at 23. And that reveals the probability of getting a random t less than the t statistic that I calculated is 0.012. And the two numbers agree, so that makes me feel confident that I'm doing the right thing. If I get a difference, it might be rounding error, so you need to be careful. You only want to do, if you get a difference in result, you should be very careful, because the AP examiners will grade the weaker answer. So you want to check your work in that situation. Now we come to the interpret section. Because the p-value 0.012 is less than alpha equals 0.1, we reject the null hypothesis. And we say there is convincing evidence that the true mean length of the 6-inch subs at this restaurant is less than 6 inches. When we reject the null hypothesis, we find convincing evidence that the alternative is true, but I have to write it in context. So that's how I interpret it. And you're likely to face a question like this now. Given your conclusion A, what kind of mistake, type 1 or type 2, might you have made? Pardon my guinea pigs in the background there. Since we rejected the null hypothesis, the error that we might have made must have been a type 1 error, because in a type 1 error, the null hypothesis is true, but we rejected it. So, because we rejected the null hypothesis, it is possible that we made a type 1 error. In other words, it is possible that we found convincing evidence that the mean length was less than 6 inches, when in fact the mean length is not less than 6 inches. Had our conclusion been in the other direction, had our conclusion been that we failed to reject the null, then we might have made a type 2 error. So, one little point here. Confidence intervals and two-sided test statistics should always give us the same conclusion. You'll see that in some of our problems. How to analyze inference problems. We're going to use the ICCI method, and this slide tells you exactly what we want in our FRQ questions. That's all I have for today. Thank you very much.